my kids and it falls. Oh, I'm recording. Sorry, I'll save that story for later. All right, so here's a problem. We want to find the internal axial force, shear force, and bending moment at point C. So again, let's imagine I'm going to cut the structure here at C, and let's investigate the two free bodies we create. Let's look at the one here on the the right to begin with. In terms of reactions, do I get to save any work? Well, they both have reactions. They both have distributed loads. So far it seems balanced. However, look at the one on the right. What shape would the one on the right be? Trapezoidal. The one on the left would always be triangular. So you probably recall from statics that triangular force is going to be a little easier to deal with than the trapezoidal force. So we're going to use the left-hand side. So that means I only need the reactions at A to get started. So let's come over here and draw us a free body diagram for the whole structure. And I'll assume I have a Y force at A, a Y force at B, and an X force at A. You can see the actual force distribution is triangular. I'll just kind of sketch that in. But we're going to replace that with a concentrated equivalent force. And what is that concentrated equivalent force? Well, it's the area under the curve. You're basically integrating. So it's a triangle, so it's 1/2 the base, which is 18, times the height, which is 3, and that should be 27. So I'm going to have a concentrated equivalent force of 27 kips. And where is it located? Remember, the centroid of a triangle is always 1/3 the base from the big end. So 1/3 of 18 is 6, and it would be 12 on this side, depending on which way you want to go. So at this point, I'm ready to solve it. Remember, I want AY, so it's probably going to be important for me just to get the reactions there. So I'll sum moments at B, the roller. Now when I sum moments at B, my concentrated equivalent force is creating what kind of moment about B? Positive or negative? Positive. So I have 27 kips times 6 feet. That's the moment arm. And then my AY reaction creates negative moment. And it has a moment arm of 18. So AY should be equal to 9. That makes sense. And I'll go ahead and check, which is an easy one to do. If I sum forces in the x direction, make sure they're in equilibrium. All I have on the whole structure is AX, so AX is 0. So now I'm going to come over here and I'm going to draw my free body diagram for the section from A to C. I'll draw it a little bit bigger so we'll be able to see all the details. So here's the 6-foot chunk of the beam. I have my A reactions at A, which in this case are 9 kips and 0. Now I have to find the height of this triangle here. So what's the intensity of the load there? Well, we can use similar triangles. I know it's 3 kips per foot for 18. So what would this height be for 6? That's 1/3 of the distance. So it should be 1/3 of that. This should be 1 kip per foot. Everybody see that? Yes? No? Maybe?
Yes, sort of.
Yes, sort of what? What's the sort of part? Here, let me try this. I'll sketch it in. Maybe you'll see it better.
Yeah.
So if I want to know this height here, which is really this small triangle, see, these triangles are similar. So the big triangle height, 3 to 18, should be what to 6? 1 to 6. So once I have that, then I can come back and compute this concentrated equivalent of this portion of the load. So again, it's 1/2 base times height. So it's 1/2 6 times 1, which is just 3. What's the distance from the cut? What's 1/3 the distance, or 2 feet? So I think that's all I need for that part of the free body diagram. Now what else do I need? Well, I need to establish my positive axial force, my positive shear force, and my positive bending moment. So there's a complete shear force, a complete free body diagram. So now just apply the equations of equilibrium. So we'll start with summing moments at the cut. Make sure it's in equilibrium. Right hand rule. So what kind of moment is this moment with my right hand rule? Positive. How about the 3 kip? Positive about the cut or negative? Positive. What's the moment arm? 2 feet. Then you slide over, you have this this 9 kip force at A, which creates negative moment and has a moment arm of 6. So what is the moment at C? This is 54 minus 6 is 48. That sound right?
Yes.
So this should be 48 kip feet. And it came out positive, so what kind of bending moment do I have? Positive. Does it make sense that the bending moment here at C is positive? I think if you look at this, you'll find it deflects something like that. And again, you can see the whole beam is probably positive bending moment. So let's finish it up and look at the shear force. So I'll sum forces in the y direction and make sure that's in equilibrium. I'll assume up is positive. So starting here, this force is down, minus V. 3 kips is down, and 9 kips is up. So it looks like the shear force is going to be equal to 6 kips. And it also came out positive. So that means at C, I have a positive shear force at 6 and a positive bending moment of 48. So any questions about that? We're out of time right now, but if we had some more time, I would show you how to do the right-hand side. It would be a little more effort, not much, but you should get exactly the same values. So you should make your choice of whether you're working the left side or the right side strictly on how much work you have to do. And I think we use a lot less work to do the left-hand side. So any other questions? Okay, I'll stop this.